So now that you've seen the different radical rules, the product rule, the addition rule, all of that, we're ready to actually start some examples of simplifying here. So what I want to draw your attention to is simplifying doesn't always mean decimal. If I have the square root of 50 and I plug that into my calculator, I end up with a really long decimal. 7.071, blah, blah, blah. Now, the decimal it doesn't even look more simple than the square root. So when we simplify these radicals, instead what we're going to do is we're going to break up this radical into its perfect square factors. Now, it sounds like a lot of math, mumbo jumbo, but here's really what I mean. We're going to figure out if there's any perfect squares that multiply with another number so that we end up with 50. So I have a list of the first 50 perfect squares here. The perfect squares are 1, 4, 9, 16, 25, 36, etc. So the perfect squares are what are on the left side of each box. Their square roots are what are on the right. So we'll come back to the square part later. What I'm really looking for is, does 9 divide evenly into 50? 50 divided by 9. No, I end up with a long decimal, which means it doesn't go in evenly. So let's try some other ones. Does 16 go in evenly? No. Shorter decimal, still got a decimal, so I don't like it. We'll see when I try 25, I finally end up with a whole number, so I can set this radical to look more like the square root of 25 times the square root of 2. This is the product rule. I can break up or put together these factors and I have the same thing. Well, how does this help us? 25 is a perfect square, you guys. The square root of 25 is 5, so this cancels out to a whole number. The square root of 50 can be simplified as 5 square root of 2. Let's try another one. Square root of 300. Now, when I take out my perfect square chart, I can see that 100 is another one of our perfect squares. Well, 300 can be broken down into 100 times 3. 100 is a perfect square. Okay, it simplifies to a whole number of 10. So square root of 300 in total can be simplified to 10 square root of 3. All right, so this worked out nicely for us. We were able to find some perfect squares that work. Notice 25 was the biggest perfect square that I could use, and really the only perfect square that I could use. 100 was the biggest perfect square I could use. So let's say, is there another way that we can figure this one out? It's a really big number under the square root, so I'm going to show you an alternative method to also get the same answer. When you can see a perfect square that'll fit easily, I recommend using a method I used at the top. When the number is large, I recommend using this method. So let's think about what numbers, doesn't have to be a perfect square, which numbers in general will multiply or divide evenly into 3,675. 3675. Let's try an easy number like 5. Awesome. 5 goes in, and so does 735. So I found two numbers that multiply back to what I started with. Now, square root of 5, I don't have any factors of that besides 5 and 1, so I'm stuck at the square root of 5. I cannot simplify that anymore. I can't find any products besides 5 and 1. So I'm just going to circle that so that I know I have to stop at that branch. However, 735, I can keep going. Let's try again by 5. 735 divided by 5 gives me 147. Again, I can stop at the 5. 147, I might be able to go a little bit farther. Let's keep going. Let's try 147 divided by 7. Tried 7 because it ended in a 7. All right, perfect. I got 21. So 147 breaks down into 7 and 21. All right, 7 is a prime number. Its only factors are 7 and 1, so I stop there. At the 21, I can keep going. 21 divided by 7 is 3, so 21 can be broken down into 7 and 3, both of which are prime, so I'm able to stop this. This is referred to as a factor tree. I'm able to stop this prime factorization tree, and I've circled all of my prime factors. Now, we're taking a square root. So whenever I have a double of a prime, like 5, I have a double. 7, I have a double. I can pull out a 5 and a 7 to the front of the square root. Notice I put a multiplication symbol in between them. That's because numbers that are inside the square root are being multiplied, so when I pull them out, they're still being multiplied. Okay? The only number that was left, flying solo, is the square root of 3. So 3,675 can be simplified to 5 times 7, square root of 3. We know 5 times 7. 35 square root of 3 would be our complete final answer. Is it easier when we can see the perfect square out front? Absolutely. Is it still, similar process this way? Of course. Takes a little bit more effort to get there, but we can still get there. I have 3 more examples for you. What happens when I try to simplify with a number already out front? I want you to forget about this 9 for 1 second and just worry about breaking down the square root of 20. The square root of 20 can be thought of as the square root of 4 times the square root of 5. Well, the square root of 4 is a perfect square. It simplifies to a whole number of 2. Square root of 5, however, is stuck. Now, we had a 9 out front before, and just like in the last problem, numbers outside are multiplied together. 9 times 2 is 18. 18 square root of 5 is my final simplified answer. So when you have a number out front, don't worry about it until you've simplified the square root piece. So there's 2 more that I want to talk about. I briefly want to talk about the difference between, first, the negative being inside the square root and the negative being outside. Now, when there's a negative number underneath a square root, this is something that you've talked about in Algebra 1. So if I do the square root of negative 121, my calculator has a mental breakdown. It says error, non-real answer, aka I end up with an imaginary number. For the purposes of the assignments that I have you do, whenever there's a negative number underneath the square root, we get an answer that does not exist. When the negative is under the square root, it does not exist. However, when the negative is outside the square root, just like what we did in the 9 with this example, I want you to worry about that negative sign at the very end of the problem. What is the square root of 121? Well, if we took a look at our factor sheet, square root of 121 is actually a perfect square. It's 11. So we know the square root of 121 is 11. We're just going to tack a negative sign onto our final answer. So there is a very big difference when the negative is inside versus when it's outside. So be on the lookout for that. The very last example has to do when we throw a variable in there. However, it's really not that scary. So what I want you to think about is when I take a square root, and when I'm squaring something, that's like addition and subtraction, or multiplying and dividing by the same number. They cancel each other out. So, pulling this kind of away, if I take the cube root of something that's being cubed, or the 9th root of something that's taken to the 9th power, in any of these cases where this number is called the index, where the index and the power are the same value, and in this case we can assume there's a 2 there, what happens is everything cancels out. So you're just left with the variable. When the index and the power are the same value, I end up with just the variable.